Hey guys, welcome back to another part of the video walkthrough of Richard Song's AP Calculus AB Chapter 2 Limits and Continuity part. And today we're going to talk about how you're going to solve limits without the need to graph now. Now, when a question like example 8 appears where they give you a piecewise function f of x, where f of x behaves like 3x squared minus 2x plus 1 when x is less than 1, and x cubed plus 1 when x is greater than or equal to 1. And they're going to ask you to find the limit of f of x as x approaches 1. Before, what we would have done was to graph the piecewise function, figure out what the graph would look like, specifically near the x equals 1 area of the graph, and we would give you an answer that way. But we're going to now introduce the fact that you have enough tools to solve these kinds of questions without the need to graph. And so, first of all, when we're being asked to solve for the limit as x approaches a certain value, we are pretty much asking you, does a limit exist at that value? And how did we solve that? By checking to see if the left-hand limit at x approaches 1 and the right-hand limit as x approaches 1 do approach the same finite value. And so in this case, I'm going to start off by talking about the left-hand limit. And so the left-hand limit would be limit as x approaches 1 minus of f of x. But when I say 1 minus, I'm asking you for a value of x that is ever so slightly less than just 1. So a value that is less than 1. And so if x is approaching a value less than 1, we're going to say that it behaves as the first part of the piecewise function, which is that the limit as x approaches 1 minus is that of 3x squared minus 2x plus 1. And all we have to do here is just use direct substitution property to plug in 1 into where we see x, and we'll get that 3 times 1 squared minus 2 times 1 plus 1 is going to be, well, 3 minus 2 plus 1, which is just 2. So the left-hand limit is going to approach 2 as x approaches 1 from the left-hand side. But what about the right-hand limit? The right-hand limit, limit as x approaches 1 plus of f of x, is going to behave in a bit of a different way, where we're asking when x approaches a value of greater than 1. Ever so slightly greater, but still greater. And so if we were to rewrite this, we would say that limit as x approaches 1 plus, or 1 on the right-hand side, would be equivalent to that of x cubed plus 1. And again, by using direct substitution property, I get that it's just 1 cubed plus 1, which is 1 plus 1, which is 2. And so the job is almost done. I've written down the math to show that the left-hand limit equals the right-hand limit. I just need to write down that it is that way. So I'm almost done, and all I have to say is that because the limit as x approaches 1 from the left-hand side of f of x is equal to that of the limit as x approaches 1 from the right-hand side of f of x, both of which being 2, I can conclude by saying that the limit as x approaches just 1 of f of x is indeed equal to 2. Okay? And so let's use our newfound abilities on an example question, primarily something like exercise 10, where again, I'm going to give you a piecewise function broken apart at a particular x value, and I want you to find the limit as x approaches that same x value. And so for number 1 in this case, I would start off by saying that the left-hand limit as x approaches negative 1 minus of f of x, because x is approaching a value that is less than negative 1, I would say that this is equivalent to limit as x approaches negative 1 minus of x plus 2, which using direct substitution property becomes negative 1 plus 2, which is 1. What about the right-hand limit as x approaches negative 1 plus of f of x? Using a similar line of reasoning as we did for the left-hand limit, we can say that this is equivalent to the limit as x approaches negative 1 plus of x squared plus 1, which by direct substitution property becomes negative 1 squared plus 1, which is, hold on a second, 2. And so in this case, the left-hand limit and the right-hand limit don't seem to be approaching the same y values. And so by saying that the limit as x approaches negative 1 minus of f of x not equaling limit as x approaches negative 1 plus of f of x, I conclude that the general limit, or that the limit as x approaches negative 1 of f of x does not exist. Cool beans. And before we move on to the next concept in the following page, I want to talk about a very, very fun question that lies on the bottom of this page. A challenge question. Ba-ba-bum. In exercise 11, they want you to sketch a graph of the function f of x that satisfies all of the given conditions. So when I solve a question like this, the first thing I want to establish is that as long as you're following all the conditions that they give you, there is no one right answer. You can draw a graph as weird as you want, as long as it obeys all the given details about it, it could be what you want it to be. Let's start off with thinking about what a graph would look like if, as it's approaching 0 on the right-hand side, it becomes -2. In other words, that means as this function f of x, as it's approaching a value of 0 from the right-hand side, its y value is going to get closer to -2. And so that would look something like this. Where, again, I'm not telling you what the exact value at x equals 0 is. I'm also not telling you enough information that you can imply what the left-hand limit of x approaching 0 is either. All you know is that whatever the tail bit on the right-hand side is at x equals 0, it will be stemming from a y value of -2. What about when x approaches 0 from the left-hand side, which is going to be the other part of this same condition? Well, this is now the left-hand limit as x approaches 0, and it turns out that it's going to approach a y value of 1. And so what this would mean is that as this same function f of x approaches x equals 0 from the left-hand side, its y value actually trends towards 1. And so a graph would look like this. You could say that it points upwards, but the gist of it is that, again, the tail that stems from the left-hand side of this x equals 0 point should be coming from a y value of 1. Now, what about the next line of details? Well, these are exact values, and if anything, these are a bit more easier to plot down, starting with f of 0 is equal to 3. Oh, okay, that definitely falls in line with the same x value that we've been working with. But this first point on the second line is telling us that when x is equal to 0, the direct y value of this function is going to be 3. So it sits atop, colored in, at y equals 3. Okay, the other two pieces of information it tells us is that when x is equal to 3, y is equal to -2. So it's going to be another point right here. And when x is equal to -3, the y value of the function is equal to -1. So here they are, the 3 points that I should keep in mind when sketching the graph of the function f of x. Now this third line is a bit more telling. It's saying that the limit as x approaches 3 of f of x is equal to 0. Not just the left side, not just the right-hand limit, but both sides of this limit approach 0. And so at x equals 3, in particular here, the graph approaches x equals 3 from the left-hand side, and when the graph approaches x equals 3 from the right-hand side, both sides of the graph point to a y value of 0. And so we can confidently say, hey, even though the direct value at x equals 3 might not be 0, the graph on both sides point towards it. Now, before we start connecting dots here, there's a final line of conditions that we need to think about, starting with limit as x approaches -3 from the right-hand side is going to be 1. So at x equals -3, the right-hand side limit at x approaching -3 is going to be approaching a y value of 1. So it looks something like this. Whereas the limit as x approaches -3 from the left-hand side is going to be approaching -1, which is in fact where our direct value of x equals -3 lies. And so these are all the details that it needs to obey, all drawn on the graph. Our brain's creative job now is to figure out, how do I connect them while still obeying what it needs? And the answer is any way you want it to, as long as it's still a function. And so all the information that we're given could look like this. And then x approaching -3 from the right-hand side can connect with that of x approaching 0 from the left-hand side. And it could look something like, I don't know, this. And then last but not least, we can also connect that limit as x approaches 0 from the right-hand side and the limit as x approaches 3 from the left-hand side to look something like this. And last but not least, just point that outwards. And so this is one rendition of a graph that satisfies all the following conditions. But it doesn't even have to be that way. For example, I can make it go straight down. I can make none of these connect and make it still obey the given conditions. And last but not least, I could create an asymptote that exists here, and then I could drop it down from here and drop it back up like this. The point is, the world's your oyster. You don't need to make your life difficult though, but you can choose how you want this graph to look as long as you're doing the things they tell you to. So again, graph could look something like this, with maybe even a straight connection between x approaching -3 from the right hand side and x approaching 0 from the left hand side. And last but not least, maybe a straight line from x approaching 0 from the right hand side to x approaching 3 from the left hand side and continues onward straight, let's say. So this is another type of rendition this graph could obey, okay?